Hey guys, just going to talk about distance traveled as it pertains to these vector-valued functions or these parametric equations that we've been looking at, and we really want to think about us being prepared to answer questions like 2b on the mock AP that you should have. So don't worry about getting that out in front of you right now, but we are going to talk about it very briefly at the end of this, hopefully short screencast. I'm going to try to be brief. Okay, so let's just suppose that we have some curve in that like looks like this. I know all my curves look like that, but let's suppose that this is some parametric equation, right, where the position is given by the position is some function, right, of x of t and then y of t, right, where they're both functions of t sort of moving independently, right? And we could find all kinds of things here, right? You guys could find velocity in general. You could find velocity at a specific point. You could find the speed from that velocity. You could find the acceleration from that velocity, right? We're just taking derivatives just like you think you would, right? And again, right, speed is something they're probably going to ask you about, and that's the magnitude of the velocity, right, with the Pythagorean theorem. And the arc length is actually going to look fairly similar to that. So let's think again, right, about if I wanted to find the distance traveled between A and B out here, and let's zoom in and pretend this is much smaller than it I'm drawing it here, but let's pretend we tried to find the distance here between 2 points. Okay, and we sort of labeled these points dx and dy, right? Sort of how far I'm moving, right? How far I'm moving in each of these directions. And we want to think about how we're doing this over a very small time, right? And obviously this is going to head towards an integral at some point. So let's zoom in right there, right? Here's my 2 points, right? And we're going to try to estimate the length of this red arc when really we're going to do that with a straight line here, right? And we're saying we move x dx here and dy here. And if we think about what dx is, right, that's the range in the rate of change, right, times some time that we're sort of we're sort of traversing, right? So we did this whole thing, right? Pretend that we went from this point C to D, over time t, right? So went from C to D in dt time, right? That's sort of the tiny little differential, or that tiny little piece of time that we went from C to D, right? So what that dx is, right, that's the rate of change at the rate of change here, dx dt, times that time, times dt. I know that looks kind of silly, right, because those dt's, in theory would cancel. And we could say the same thing for dy dt, times dt. Okay, right, because that's the rate of change times the time, right? That's sort of how far we went. And if we wanted to find the length of that segment connecting CD, and we're saying that's a pretty good approximation as we get really small, really close to the length of this curve, right, that would just be the square root of, right, by the Pythagorean theorem, this thing squared plus this thing. Oops, forgot another dt. This thing squared, right? It's just those two things squared. That's what the Pythagorean theorem would say, right? And we're going to do something very similar to what we did in the past, right? I'm going to factor out a dt squared, right? Factor out a dt squared. So that's going to be something like dt squared times dx dt squared plus dy dt squared. Right? And since I have that under the square root, I can really pop that dt out, right? And what is dx dt? Dx dt is simply the derivative of position. So we could write this either way, right? We could write that either way. We could say this is dx dt squared plus dy dt squared times dt, again, outside the square root, or you could say, right, this is sort of x prime squared plus y prime squared dt. Those are the same things. We've sort of been using them interchangeably. Okay, and what do we need to do? We just need to sum this up from a to b, right? So that sounds like an integral, right? So that sounds like an integral. So we're going to have the integral from a to b, because, right, this is just one of these tiny little segments. We need to have all of them, right? A to b times the square root of dx dt squared plus dy dt squared dt, right? That's the sum from a to b of all of those things. So it's just this integral, and that's sort of the distance traveled, right? This thing right here is the distance traveled from a to b, Okay, so this is a formula that we have to have memorized. There are not too many of them, right? It looks very similar to the regular arc-length formula, square root of 1 plus dy dx squared. It looks very similar to that. We can talk about sort of similarities in the future. But this is something we have to have memorized. And if you're happy with this, you can either apply it to one of two examples, right? On the mock AP, right, we saw 2b, I think it was, asked the total distance traveled from the laser from time t equals 1 to time t equals 3. Right, so that thing, just to refresh us, it looked like this, and dy dt looked like this, and this could be a good exercise for those of you that don't know how to use your calculator right now, sort of review Miss Boyer's directions, right? But we're simply going to say, right, that this thing is the integral from 1 to 3 of these two things squared, right? These two things squared. So 3 cosine t squared plus 4 cosine 2.5 t squared dt. And if you punch that into your calculator, you should get something like 7.090. Okay, radians mode as always. And this is all that is, right? So this is really a freebie set of points, right? We probably get a point for writing this expression on the left and a point for getting this guy on the right. So that's, freebie as long as we can remember that formula, and it's a good chance that they'll ask that, right? They love asking about speed, and about arc length or distance traveled, okay? So I hope that was clear. Feel free to be done if this makes sense. If you want to see me work through one more example, the classic example here is if I have x of t as cosine t and y of t as sine t, well, this, of course, will trace out the unit circle. Convince yourself of that right now, right? If you plug in 0 for t and pi over 2 for t and such, you can see that you would trace out the unit circle, right? So let's say distance traveled in quadrant 1, right? So that's going to be sort of from here to here, right? So we're going to look at this distance traveled, and we can, in our head sort of think about what that would be. Well, we can do that really quickly, right? That distance traveled d is going to be the square root of dx dt squared plus dy dt squared dt, and then we're going to need to slap an integral around it, right? Where we're going to want to go from 0, right? Here t is 0, and up here t is pi over 2. This seems like polar coordinates, but it's not, right? It's not polar coordinates. We're going to be going from 0 to pi over 2 because those are the values of t that trace out that path, right? And this is a fairly simple integral to take, right? Because we're going to have stuff fall apart, right? So dx dt, that's just negative sine t, the derivative of cosine, squared. Dy dt, that's just cosine t squared dt, and all under a square root, I should say, all under a square root. And that thing, of course, is just going to be sine squared plus cosine squared, right? Because the negatives are going to cancel. So that actually is just the integral of 1. That's why I said this was going to be fairly easy, right? But we can see sort of where these things come in, right? This isn't actually a tricky integral to take. Obviously, there could be things where either required to do with calculator, like 2b up above, or something that had an interesting integral. They could incorporate all kinds of fun u sub or something weird into here. And we'll see plenty of examples in the coming weeks about this. So, this thing, right, is just t, right? And so, you guys can take this, right? You're just going to get pi over 2, which, of course, the circumference of the circle was diameter 2 times pi. So this pi over 2 for a quarter of it makes total sense. So that's sort of a brief intro into distance traveled in parametric world or vector valued world. Okay, so I hope that was informative. I hope I kept it relatively short. I think relatively short. And this is sort of going to suffice. We'll see it in class, but I'm not going to really teach this in class now. All right. Hope you guys enjoy the rest of your weekend.